Hi students and friends, this is your host and teacher Sayyid Ayazuddin Haider. You are watching Learn and Teach by Sir Ayaz. So I'm continuing my O-level past paper session and I'm done till 42 for IGCSE. So I will continue for IGCSE and this time I've selected 43. It's of October, November 2024. I'm not going to read the formality, that is time is 1 hour 15 minutes. It's paper 4 theory. You can use calculator, it's 80 marks. Periodic table will be printed in the paper. So let's start with question number 1. A list of substances is shown. We have bauxite, carbon dioxide, cryolite, ethane, ethanol, ethene, graphite, helium, hematite, hydrogen, silicon peroxide, sodium chloride. Answer the following questions using only these substances from the list. Each substance may be used once, more than once, or not at all. State which substance is manufactured by fermentation. So during fermentation, glucose is fermented to produce ethanol and carbon dioxide. And if you see the list, both carbon dioxide and ethanol are present in the list. So you can either write carbon dioxide or ethanol. Main product is ethanol. But both are the products of this reaction. B is monoatomic. You know that there's a group 8 element. We have helium, neon, argon, krypton, xenon, radon, organon. Organison. These all are monoatomic. And if you look at the list, you can see only one element from this group, which is helium. So you're going to write helium here. Archie is a reactant in photosynthesis. You know, in photosynthesis, carbon dioxide and water are reactants. So you'll find only carbon dioxide here, which is one of the reactants. So I'm going to write carbon dioxide. D is a solvent in the extraction of aluminium. In the extraction of aluminium, the electrolyte used is alumina. It has very high melting point. In order to reduce its melting point, or you can say decrease operating temperature, as well as acting as a solvent in which this aluminium easily dissolves. It's cryolite. Cryolite is the one which is used as a solvent here. So you write cryolite. E is an ore of iron. This is something which you have to learn if you look at the list. This is hematite. This is the ore of iron. So I'm going to write hematite. F is manufactured from methane. Now when methane is treated with steam, you will get hydrogen gas. Is treated with steam, we get hydrogen and carbon monoxide. So hydrogen is there in the list, so I'm going to write hydrogen here. Moving to next part, which is part G, is a compound with a giant covalent structure. They are saying compound, not the element. Giant covalent structure. We have giant covalent structures here. One is graphite, giant covalent structure, silicon peroxide. These two are giant covalent structures, but they are saying compound. So it must be silicon peroxide. H is used as a lubricant. We have only one element which is used as a lubricant here, it's graphite. Used as a lubricant because of the presence of intermolecular force or weak forces between the layers. The layers can slide. So you write graphite there. Last one is tested for with lime water. You know, only one gas is tested with lime water, that is carbon dioxide. Carbon dioxide we have already used one time, so I'm going to use it for the last time, that is carbon dioxide. Lime water is used to test this gas. Going to next question, which is question number 2. This question is about electrolysis. A. State the meaning of the term electrolysis. Electrolysis, it's divided into two terms. We have current and breakdown. Lysis mean breakdown. Mean breakdown. And electro means current. So we have breakdown by passing an electricity. Breakdown by passing an electricity. Of what? Of an ionic compound. Of an ionic compound. In molten or aqueous state. Next part B, table 2.1 gives some information about the electrolysis of two electrolytes using graphite electrodes. Here's table 2.1. You have electrolyte concentrated aqueous potassium iodide. Then you have aqueous copper 2 sulfate. 1. Complete table 2.1. Now we need to complete this table 2.1. So for the electrolyte concentrated aqueous potassium iodide, the observation at anode, it must be due to the formation of iodine. This is concentrated. That's why iodine will be produced due to the higher concentration of iodide ions. So solution will turn to brown or black solid. Brown solution or black solid. Both are correct. And the name of the product is iodine. What about cathode? You see bubbles of colorless gas. It must be hydrogen. Why? Because potassium, it will never get discharged. It has very high difficulty of discharge or low ease of discharge. But you can even say that it's highly reactive than hydrogen. So for aqueous copper 2 sulfate, they are asking us to write down the product at cathode, which is pink brown solid. It's none other than copper. Part 2. Oxygen is produced at the anode by the electrolysis of aqueous copper 2 sulfate. Write the ionic half equation for this reaction. So you have hydroxide ion in the aqueous state. We write negative, and it gives oxygen gas plus water, H2O, in the liquid state plus electrons. Now I'm going to balance it. We have two atoms of oxygen gas on the product side, as well as one oxygen atom attached to hydrogen in water. So I can't place 3 before OH negative ion because this will not balance hydrogen also. So we need to put even number. So what about 4? If I'll place 4 before here, OH negative ion, then I will write 2 before 2H2O. It's balanced now. Now what about electrons? 4 OH minus, which means it's losing 4 moles of electrons. So I will write 4 before E minus. C. Aqueous copper 2 sulfate is electrolyzed using copper electrodes instead of graphite electrodes. 1. Explain why the mass of anode decreases during this electrolysis. Now anode, it dissolves. It dissolves. Why? Because there is a loss of Cu2 plus ion in the solution that will be compensated. And how this is going to be compensated? Anode is going to dissolve. So you can write anode from anode. Anode is made up of copper. So it will form Cu2 plus ion. Anode forms, dissolves, forms Cu. If you are writing dissolves, then you will write dissolves to give. Dissolves to give Cu2 plus ions in the solution. Moving to the next part, which is part 2. Name the product formed at the cathode. You will get copper at the cathode. So I'll write copper here. Part 3. State what change, if any, is observed in the appearance of the aqueous copper 2 sulfate. So what will happen to the change? So copper 2 plus ions depositing at the cathode, and in order to compensate this loss, the copper anode is dissolving to give Cu2 plus ion back into the solution. So there will be no change in the appearance of aqueous copper 2 sulfate. It will remain as it is in the solution. It's actually blue in color. So you will write no change here. Move to next question, which is question number 3. This question is about compounds of tin. A, tin 4 oxide has a formula SnO2. The relative formula mass Mr of SnO2 is 151. Calculate the percentage by mass of tin in SnO2. So we need to know the AR of tin because relative formula mass is already provided. I need AR of tin. Here is tin in the periodic table. It's in group 4. And AR is 119. So 119 percentage. We'll multiply 119 by 100 and divide it by relative formula mass Mr, which is 151. The answer will be 78.8%. This will be the final answer. Moving to the next part, which is part B. SnO2 is an amphoteric oxide. SnO2 reacts with aqueous sodium hydroxide, NaOH, to form a solution. To form a sodium salt and water only. The sodium salt contains a negative ion with the formula SnO3 2 minus. Number 1. State the meaning of the term amphoteric. So amphoteric oxide is the one which reacts with both acids and with bases to produce a salt and water. It reacts with acids and with bases to produce salt and water. To produce salt, and water. Number 2, write the symbol equation for the reaction between SNO2 and NaOH. They are asking us to write down the reaction equation. Here's the reaction equation. We'll be getting sodium salt and water only. The formula of water is, you know, that H2O. What about the sodium salt? Sodium, it's carrying SNO3 2 minus N. So we have Na and SNO3. The valency for SNO3 is -2. Sodium, it's in group 1, it's sodium. It must be having +1 valency. So I'm going to write +1 here. Ignore the charges. These numbers will be swapped. So you will be getting Na2SNO3. Na2SNO3. This will be the final formula for the sodium salt produced here. Let's balance this equation. So if I'll write 2 before NaOH, now count the number of atoms. Sn, we have 1 atom of Sn on both sides. What about oxygen? 2 plus 2, 4. On the right hand side, we have 3 plus 1, 4. It's balanced. What about Na? 2 Na, reactant product, both are balanced. Hydrogen, H2O, it's also balanced. Moving to next part, which is part C. Clean is a metal that forms both covalent and ionic compounds, such as why this is unusual for a metal, because metals, they form ionic bonds or ionic compounds only. Metal forms ionic bonds or ionic compounds only. We're moving to next part, which is part D, D1. Tin 4 chloride SnCl4 is covalently bounded. A tin atom has 4 electrons in its outer shell. Complete the dot and cross diagram in figure 3.1 for a molecule of SnCl4. Show the outer shell electrons only. So first of all, I'm going to show you the key on the right hand side. We have Sn. Let's consider cross as valence electron for tin and dot for chlorine. Now they have already mentioned there are 4 electrons in the outer shell of Sn. Looking at this diagram, so Sn is going to share each 1 electron with each of these chlorine atoms. So 1, 2, 3, 4. What about chlorine? Here is chlorine. Chlorine is in group 7, which means it must have 7 valence electrons. So I'm going to show the 7 valence electrons of chlorine. Each chlorine. 1, 2, 3, 4, 5, 6, 7. Now this one, 1, 2, 3, 4, 5, 6, 7. This chlorine, 1, 2, 3, 4, 5, 6, 7. Last one, 1, 2, 3, 4, 5, 6, 7. All done. This will be the final dot and cross diagram. Moving to next part, which is part 2. Tin 2 oxide SNO is ionically bonded. The melting points of SnCl4 and SNO are shown in table 3.1. Here is table 3.1. The melting points of both SnCl4 and SNO is provided. Explain in terms of structure and bonding why SnCl4 has a much lower melting point than SNO. Now, this question is of 3 marks. So you can write statements either for SnCl4 or SNO2. Then compare the forces between these two. For example, if you are writing for SnCl4, how are you going to write? If I'm going to write for SnCl4, looking at the melting point, it's a simple molecules having intermolecular forces or attraction between molecules, intermolecular forces or attraction between molecules in S and Cl4. Then you can write attraction in S and Cl4 is weaker. Attraction in S and Cl4 is weaker than S and O. You can have a reverse argument like SNO, the attraction in SNO is stronger than in SnCl4. Now, next statement must be about SnO2. And that is you have to write its giant ionic structure or lattice. Giant ionic structure or lattice. SnO2. In this way, you will gain all these 3 marks. Moving to the next part, which is part E. Part of the reactivity series is shown. We have magnesium, aluminum, tin, copper, and the top we have most reactive one. And below we are having least reactive. Here, copper is least reactive, magnesium most reactive. 1. When aluminum foil is added to aqueous tin 2 sulfate, a reaction does not occur even though aluminum is above 10 in the reactivity series. Explain why a reaction does not occur. You see, aluminum is above 10, but the reaction does not break. So what's the reason? So it's definitely forming some kind of impermeable layer. So you can write a layer of unreactive oxide form on Al. A layer of unreactive oxide form on aluminum. This is typical of aluminum. That's why it prevents its further reaction. Part 2. An aqueous solution of tin 2 sulfate contains Sn2 plus ions. 2 experiments are carried out. Experiment 1. Copper is added to aqueous tin 2 sulfate. Experiment 2. Magnesium is added to aqueous tin 2 sulfate. Write in ionic equation for any reaction that occurs in each experiment. If no reaction occurs, write no reaction. So experiment 1. Copper, you are adding copper to aqueous tin sulfate. If you look at the position of copper and tin, it's below. Copper is below tin. Copper below tin. So definitely reaction is not going to happen. So you are going to write no reaction in case of experiment 1. Experiment 2. Magnesium is added to aqueous tin 2 sulfate. If you look at the position, magnesium and tin. Magnesium is above tin. Magnesium above tin. So definitely this reaction is going to happen, and they are expecting us to write down the ionic equation. Only you have to write ionic equation. So in the ionic equation, you have to cancel out the common ions, which is known as spectator ions. So here, magnesium during its displacement reaction with aqueous tin to sulfate forms magnesium sulfate and tin. Sulfate is the common ion or spectator ion on both sides of the equation. So we won't be having any sulfate ion in this ionic equation. So I will write magnesium. You're reacting magnesium. So you have to write Mg in solid, Mg solid plus tin. Tin must be carrying +2 charge. It's aqueous solution. Now magnesium get oxidized or react or displace tin from tin to sulfate. So it will form Mg+2 ion aqueous. On the other hand, tin will get reduced, that is from Sn+2 to Sn. You will get Sn solid air. This will be the final ionic equation in this case. F. Hydrated tin 2 nitrate SnNO3 whole twice dot 20H2O decomposes when it is heated. One, state what is meant by the term hydrated. Now in this, water is chemically combined with the substance. Water is chemically combined with the substance. Or you can even write contain water of crystallization or containing water of crystallization. Part 2. Complete the equation for the decomposition of SnNO3 whole twice dot 20H2. So they want us to balance this. So what I will do, I'm going to write 2 before SNO. It's balanced now. What about water? 20 multiplied by 2 is 40. So I will write 40 before H2O. What about NO2? So nitrogen on the left hand side, 2 multiplied by 2 is 4. We have 4. We have 4 moles of NO2. So I will write 4 before NO2. Let's count the oxygen. So you have 3 to the 6. 6 plus 20. 26. 26 multiplied by 2 is 52. So you have 2 plus 4 to the 8. 8 to 10. 10 plus 2 is 12. Yes, 12 plus 40 is 52. Oxygen is balanced. Equation is balanced now. Moving to next question, which is question number 4. This question is about sulfuric acid, H2SO4. A. Dilute sulfuric acid and aqueous sodium hydroxide can be used to prepare sodium sulfate crystals using a method that involves titration. The apparatus for titration is shown in figure 4.1. So this apparatus we are using. We have 20 centimeter cube of aqueous sodium hydroxide in the conical flask and dilute sulfuric acid in the burette. Thymophthalein is used as an indicator for this titration. Number 1, state the color change of thymophthalein at the end point of this titration. This is something which you have to remember. So in alkali, it must be blue. So you are having alkali initially, and the alkali you are going to add acid. So the final color must be in acid. So it's turning from blue to colorless. So it's colorless in acid. Blue to colorless. Number two, suggest why universal indicator is not used for this titration. You may have too many color changes here. Part B, 25 centimeter cube of aqueous sodium hydroxide NaOH of concentration 0.1 mole per dm cube is neutralized by 20 centimeter cube of dilute sulfuric acid H2SO4. The equation for the reaction is shown. Here's the reaction equation. 2NaOH plus H2SO4 gives Na2SO4 plus 2H2O. Calculate the concentration of H2SO4 using the following steps. Okay. So first they are asking us to calculate the number of moles of NaOH used. The strength of sodium hydroxide is given, which is 0.1 mole per dm cube. 0.1 mole per dm cube means it's 0.1 mole in 1000 centimeter cube. And the volume used is 25 centimeter cube. So I will write 1000 centimeter cube contains 0.1 mole. Therefore, 25 centimeter cube contains X mole. Do the cross. So equation becomes X is equal to 0.1 multiplied by 25 divided by 1000. 0.1 multiplied by 25 divided by 1000. So answer must be 0.0025 moles. 0.0025. These are the moles of sodium hydroxide. Determine the number of moles of H2SO4 that reacts with the NaOH. Now we need to calculate the moles of H2SO4. According to the reaction equation, 1 mole sulfuric acid reacting with 2 moles of NaOH. Therefore, X mole react with 0.0025 moles of NaOH. Do the cross, the equation becomes like this: X equal to 0.0025 divided by 2. And the answer will be 0.00125 moles. 0.00125 mole and of H2SO4. Now we have the moles of H2SO4. Calculate the concentration of H2SO4. So these are the moles in 20 centimeter cube. So 20 centimeter cube contains 0.00125 moles. Therefore, 1,000 centimeter cube contains X moles. Do the cross. What you will get? You will get X is equal to 1000 multiplied by 0.00125 and divided by 20. So we will get what? 1000 multiplied by 0.00125 divided by 20. 0.0625. 0.0625. See, a student is provided with an aqueous solution of sodium sulfate. Describe how to prepare a pure sample of sodium sulfate crystals from this solution. You will definitely start by heating the solution to saturation. I will write heat to saturation. Heat the solution to saturation point. Next step will be crystallization. So I will write crystallize or cool down. Last but not least, description of drying. Description of drying. That is, you can dry in air, oven, or you can even use tissue paper. D. Potassium hydrogen sulfate, KHSO4, can be prepared by a reaction between aqueous potassium hydroxide and sulfuric acid. Water is the only other product. Write a simple equation for this reaction. The reactant is sulfuric acid and potassium hydroxide. You know the formula of potassium hydroxide? It's KOH. K is in group 1. OH carries -1 charge. That's why the formula must be KOH. H2SO4, it must be sulfuric acid, H2SO4. Now, one of the product is KHSO4. They have already gave the formula. So you write KHSO4 plus H2O. This will be the final equation for this reaction. E. Potassium hydrogen sulfate, KHSO4, dissolves in water to form solution X. Solution X contains K plus, H plus, and SO4 2 minus ions. Number 1, name the type of solution that contains H positive ions. It's acid or acidic. You can write acid. Even acidic is also acceptable. Number 2, state the observations when the following tests are done. A flame test is carried out on X. You see X containing K plus ion. So flame test U2 K. So potassium. So it will give lilac color. So I'm going to write lilac here. U2 potassium ion. Solid copper 2 carbonate is added to X. Now you are adding metal carbonate to X. X is containing H positive ion, so it must be the reaction between acid and metal carbonate. Acid plus metal carbonate. So what you have to do, you have to write all the observations whenever acid reacted with metal carbonate. So you'll have solid dissolving. So you'll write solid dissolves during this reaction. You will get 3 products: salt, water, and carbon dioxide. Carbon dioxide produce, so it will give effervescence or bubbling. Effervescence or bubbling. Last observation, it must be the color of copper 2 plus ion. The copper 2 plus ion is forming a salt. So it means solution will turns blue. Solution turns blue. Into the salt of Cu plus 2. Aqueous barium nitrate is acidified with dilute nitric acid is added to X. Now barium nitrates used to test the presence of this sulfate ion, and it will give white precipitate. So I'm going to write white PBT here. Part F, 0.325 gram of zinc is added to dilute sulfuric acid, which contains 0.01 moles of H2SO4. The equation for this reaction is shown. Zn plus H2SO4 gives ZnSO4 plus H2. Number 1, determine whether Zn or H2SO4 is the limiting reactant. Explain your answer. So what I'm going to do, I will convert the mass of zinc into moles, as moles of H2SO4 is provided, and we are also provided with the reaction equation. So it will become easier for us to compare the moles in order to find the limiting reactant here. So moles of zinc, moles of Zn, you know the way, you simply have to divide the mass by the AR of zinc, which is, here is zinc, 65. 65 is the AR of zinc. So I will divide 0.325 by 65 and we'll get 0.005 moles of Zn. Now compare moles. Here, moles. We are almost there. See here, Zn, H2SO4. What's the relation? Moles 1 reacting with 1. So 0.005 reacts with X. So it will definitely become 0.005 moles. These are the moles of H2SO4, and compare it with the moles provided in this question. They gave 0.01 moles. We need 0.005 moles of H2SO4. And they provided us with the higher number of moles. So Zn will be the limiting reactant and H2SO4 is the reactant in excess. So how are we going to write? Zn is limiting. Zn is limiting because moles H2SO4 higher than moles Zn. Moving to next part, which is part 2. In another experiment, 48 centimeter cube of hydrogen gas H2 is produced. The experiment is carried out at room temperature and pressure RTP. Calculate the number of molecules in 48 centimeter cube of H2 gas measured at RTP. The value of Avogadro constant is 6.02 into 10 to the power 23. So in this, first of all, we need to convert the volume of hydrogen into moles. And they have provided 48 centimeter cube. So you know that at RTP 24,000 centimeter cube, which is a volume occupied by 1 mole of any gas. So here we are having H2 gas. Therefore, 48 centimeter cube, again the volume is occupied by X mole of H2. Do the cross. So you'll get what? You'll get X is equal to 20. X is equal to 48 divided by 24,000. So the moles will be 0.002. 0.002 moles of H2. Now you got the moles of H2. You can easily calculate number of molecules. You simply have to multiply these moles by the Avogadro number. So number of molecules. So we have 0.002 by 6.02 into 10 to the power 23. The answer must be 1.204 into 10 raised to power 21 molecules. Number 5. This question is about rate of reaction and equilibrium. A student investigates the rate of decomposition of aqueous hydrogen peroxide H2O2 using manganese 4 oxide as a catalyst. The equation for the reaction is shown. Here's the reaction equation. 2H2O2 aqueous gives 2H2O liquid plus O2 gas. The student uses the apparatus shown in figure 5.1. You look at the figure, we have balance here, aqueous hydrogen peroxide in the conical flask with aqueous hydrogen peroxide loosely fitting cotton wool. And then we are also having manganese 4 oxide, which is a catalyst in a small container beside this conical flask. The student adds a catalyst to the aqueous hydrogen peroxide, replaces a container on the balance, starts a stopwatch, records the mass at regular time intervals. A. Table 5.1 shows the mass recorded at regular time intervals. This is table 5.1. You see the mass at regular time intervals, the mass recorded. Part 1 suggests why the mass decreases as time increases. If you look at the equation, during this reaction, the gas is released, which is O2 gas. So, O2 gas escapes from the flask. Part 2, after a certain time, the reaction stops. Explain why the reaction stops. So definitely all the H2O2 has decomposed or reacted. So you write all the hydrogen peroxide has reacted or decomposed. You see the reaction is decomposition because it's breaking down into two products, water and oxygen. Moving to next part, which is part 3. Suggest why it is not possible to use the results in table 5.1 to determine the exact time when the reaction stops. So if you look at this, if you see this, that you see the time interval, it is large. There will be time intervals too large. That's why we can't use the results. These results can't be used to determine the exact time when the reaction stops. B. Figure 5.2 shows a graph of the mass against time. So here's the graph of the mass. The experiment is repeated at a higher temperature. All other conditions remain the same. Number 1, explain in terms of collision theory why the rate of reaction is higher at higher temperature. Now they have already mentioned that the rate is higher at higher temperature. And you have to explain, in terms of collision theory. It's of 3 marks. So you can't write the statement rate of reaction increased or rate of the reaction is higher. So you will start with the kinetic energy of particles. The kinetic energy of particles increases. Kinetic energy of particles increases. Now what else you can write? Now you refer to the proportion, fraction, or percentage of particles and include the statement higher proportion, higher fraction, higher number or higher percentage of particles. They have energy greater than or equal to activation energy. Higher number, fractions. You can even write fractions. You can even write proportions. Or you can even write percentage of particles have energy greater than or equal to activation energy. Equal to activation energy. Activation energy is represented by capital E with the base A. You will get 2 marks here. 1 mark for this one mark for this statement. Now you have to add one more statement. Now there will be higher number of particles having energy greater than or equal to the activation energy. The frequency of collision, it will increase. So you write frequency of collisions between particles increases. Of collisions between particles increases. Moving to next part. Part 2 on figure 5.2, sketch the line expected when the experiment is repeated at a higher temperature. Now you have raised the temperature. So definitely it will only increase the rate of the reaction. The total loss in mass will remain same. But what will happen to the graph? So the graph, I'm using the different color here. So the graph, it will definitely start at same mass. Graph starts at same mass, but steeper gradient. But steeper gradient. What else? The graph, it ends or level off at the same mass but earlier. Graph ends or level off at the same mass but earlier. So I will start from 0, but will have steeper gradient, means it will be like that. See, it's leveling off earlier. Must be like that. Moving to next part. C. Manganese 4 oxide is the catalyst in this reaction. 1. Explain the meaning of 4 in manganese 4 oxide. This number 4 is oxidation number of Mn. Oxidation number of Mn, that is +4. Oxidation number of Mn is +4. Don't just write 4. You have to write the charge, either positive or negative. Here it's positive, +4. Number 2, state how the mass of the catalyst has changed, if at all, at the end of the experiment. So there won't be any change in the mass. So you write no change. The mass of the catalyst will not change. The mass will remain same. Only the physical state of the catalyst changes at the end of the reaction. Part D. Nitrogen monoxide gas NO and oxygen gas O2 reacts to produce nitrogen dioxide gas NO2 at room temperature. The reaction can reach equilibrium. The equation is shown. Here's the reaction. 2NO plus O2 gives 2NO gas, and the forward direction delta H is minus, which means it's exothermic. In the forward direction, it's exothermic. So in the backward direction, it's definitely endothermic. Delta H will be positive. So you write endothermic here. NO gas and O2 gas are passed into a beaker as shown in figure 5.3. Here's a beaker 5.3. 1. Explain why the method shown in figure 5.3 will not allow the reaction to reach equilibrium. Definitely, it's not a closed system, it's an open system. For a reversible reaction reaching to dynamic equilibrium state, it must be in a closed system. Number 2, the apparatus is changed and the equilibrium is reached. The temperature of the equilibrium system is then increased and the position of equilibrium shifts to the left. Explain why the position of equilibrium shifts to the left. Definitely, if you look at the sign of the delta H, it's minus in the forward direction. And as I told you, if it's minus in the forward direction, which means it's exothermic, then backward direction, it will be endothermic. So definitely it will shift the equilibrium to the left-hand side. So you can either write forward reaction is exothermic or reverse argument. Forward reaction is exothermic or reverse argument. Moving to the next part, which is part 3. The pressure of the equilibrium system is then increased. State the direction, if any, in which the position of equilibrium shift. Explain your answer. So they are increasing the pressure, which means it will move to the direction with less number of moles. Move in the direction with less moles. Remember, it's applicable to gases. The effect of pressure is only applicable to gases. So we have gases on both sides. And on the reactant side, we have 2 plus 1. On the product side, we have 2. What are these? These are the number of moles or molecules or volume of gases. Remember, the effect of pressure will be applicable to gases only. So it will definitely shift the equilibrium to the right-hand side or forward direction. Forward or product side. So for the explanation, refer the number of moles, molecules, or volumes of gases on either side of the equation, side of the reaction. So in this case, you are having less number of moles of volume of gases on the right-hand side and high on the left-hand side. Less product side or high reactant side. Moving to next question, which is the last question of this paper. Question number 6. This question is about hydrocarbons. A. State the meaning of the term hydrocarbons. Compounds which contain carbon and hydrogen only. Compound which contain hydrogen and carbon only. B. Propene. C3H6 can be made from long chain alkanes such as dodecane. Dodecane contains 12 carbon atoms. 1. Deduce the molecular formula of dodecane. So dodecane is an alkane. You know the general formula of alkane, CnH2n plus 2. You know the number of carbon atoms here. We have 12. So value of n is 12. So you write C12. 12 multiplied by 2 is 24. 24 plus 2 is 26. H26. This will be the final molecular formula of dodecane. Number 2. Name the type of reaction that occurs when long chain alkanes are converted into shorter chain alkenes. It's known as cracking. C. Propene is an unsaturated hydrocarbon. Propene reacts with bromine. Number 1. State the meaning of the term unsaturated. Contains at least one carbon-carbon double bond. Contains at least one carbon double bond. Part 2. Write the molecular formula of the product formed when propene reacts with bromine. So it's an addition reaction and you will get only one product. If you know the formula of propene is, it's an alkene. So it must be following the general formula of alkene, which is CnH2n. We have 3 carbon atoms here. So C3H6. And if you react with Br2, so what you'll do, you'll simply add this Br2 to this C3H6. So you'll getting C3H6Br2. This is alkene, it will undergo addition reaction. That's why you're getting this formula. Part D. Styrene molecule is represented as shown in figure 6.1. Here's styrene. Number 1, the molecular formula of styrene is C8H8. Determine the empirical formula of styrene. It's very easy. Simply have to simplify it. 8, same number. It will be divided by 8. So you will get CH as its empirical formula. Simplified formula means empirical formula means simplified version or simplest formula. Simplest formula. Simplest formula means simplest combining ratio. Number 2, styrene can be polymerized into polystyrene. State the type of polymerization that occurs when styrene is converted into polystyrene. You see the double bond is here. So it will definitely go for addition. Addition, polymerization. Last part. Draw the structure of one repeat unit of polystyrene. Include all of the atoms and all of the bonds. The C6H5 group should be represented as C6H5. So it's very easy. You simply have to remove the double bond. So all the bonds become single and C6H5 will remain like this. And this will be the one repeat unit. They ask you to show only one repeat unit. Thanks for watching. Press like and share my videos. For more videos, subscribe to my channel and press the bell icon.